This is the Calstock Wall Design Project by Group 14.
First, I'm going to talk about the site plan. The site plan is required to show the surrounding area of the site where the retaining wall collapsed and to show where we will be working to replace it. It also shows where we will be storing our materials and how we will get the machinery on the site. In this case, we opted to use a boat for transporting the materials and the machinery. Retaining walls are built on sloping terrains to prevent soil erosion and to resist the lateral pressure of soil, stopping the soil and debris spilling onto property and causing damage. In this case, it is built between the area of the River Tamar and the residential area due to the difference in the heights of the soils.
One of the major reasons for the failure of the initial Calstock wall was poor draining. This led to increased hydrostatic pressure and saturation of soil. When the water accumulated over time via rainfall, it caused an increase in pressure, causing the wall to collapse. Another reason the wall failed was due to insufficient reinforcement. It wasn't designed to withstand precipitation, so while it held up against dry soil and vehicles, it couldn't withstand saturation. An assumption that can also be made is that over time, the materials in the retaining wall deteriorated due to prolonged exposure to the weather. This caused the wall to weaken and contribute to its eventual failure.
Our first rejected design was a simple Gabion box gravity wall. We rejected this design because of the lack of embedded foundations or shear keys to improve sliding resistance. Our second rejected design shows a buttress wall. The buttresses would take up a significant amount of space which could otherwise be used for more weep holes for improved drainage. Our third design shows an anchored wall, and we rejected it because it would require additional machinery to insert the anchors. Furthermore, more planning would have to take place to make sure the anchors are not destroying any cables or pipework, as homes are in close proximity to the retaining wall.
Creating our new Calstock wall design, we decided on using a slanted gabion wall as we believed this was cheaper and quicker to build. This is because we could source the rocks used in the gabion boxes from the local area, and it is important that the wall is built as quickly as possible as the failure took place on a one-way road with no other access. Another reason we decided on the gabion design was due to the fact that the previous failure took place due to a water buildup behind the wall, meaning there was an insufficient drainage solution. This water buildup increased the lateral loads and caused the sliding. However, as the gabion wall is made of rocks, the water can seep through easily. Furthermore, we used gravel as our backfill, which is permeable, resulting in no water being stored behind the wall. The gabion boxes will be made using galvanized steel wire and angular blocks of granite between 80 and 100 millimeters in size that will piece together. Also, to prevent the displacement of soil through the gabion boxes when it rains, we have implemented a geotextile membrane that will be fixed behind the wall to prevent this. In calculation, we considered the pressures from the soil and water and used that with the point loads, sliding force and resisting moments to calculate if our structure can resist the forces. The result is that it can, as our factor of safety in sliding was 1.2 and the factor of safety in overturning was 2.39.
Construction sequence part 1, we can see a site after collapse right now. Then we remove debris from the site and we start inserting temporary sheet piles. Here we assume the soil to be near to the riverbed, so it's supposed to be soft enough for steel piling. Then we excavate ground for foundation, and after excavation we remove the steel piles. We compact the base soil then and collect any leftover rock from the excavation, grind them up, and which can be used to lay foundation afterwards or fill the gabion cages. And then the last step of part 1 is to insert geotextile.
Moving on to the second half of the construction sequence, we start by building the baskets, fastening them with helicoils. Then we place geotextile sheets behind the baskets, and then we can fill up the baskets with the crushed stone. Then we can use a crawler crane to place the first layer of gabion baskets, followed by a backfill, and then we repeat steps 13 and 14 for the second, third, and fourth layer. Once that's complete, we can then pave the road using an asphalt paver.
Then we build a rock fence on top of that, and then our final design is complete.
We all know that safety features are an important part of every construction. This is why we plan to set up barriers around the perimeter of the whole construction site to prevent pedestrians from walking where they are not wanted. We will also place traffic cones to help guide these pedestrians as to where to walk and where they shouldn't. The many spaces between rocks in the gabion allow water to pass through without pooling up at the bottom, which is what caused the failure in the first place. This is another safety feature as it means that the road will not collapse in the future.